So I'm actually going to use a Biology 1406 PowerPoint for the Basic Chemistry of Life lecture, as it covers everything you do need to know without doing 180 slides over it. I thought y'all might appreciate that. So this is the chemistry of life. Here we have a bombardier beetle, which is known to create hot acidic spray when it is endangered, but without combusting itself, because it keeps the hydrogen peroxide and the other component separated in its body, and it only mixes right at the exit point of the body. Here is a phospholipid membrane, which is allowing us to have those boundaries that we have to maintain exteriorly and interiorly in the cell. And it is a huge, huge evolutionary advancement. And here are just molecules of different things showing hydrogen bonds as well as covalent bonds. I don't see any ionic bonds. Okay, why are we studying chemistry? Well, as I stated in the previous video lecture, chemistry forms biology. Physics forms chemistry. Chemistry forms biology. So biology has to follow all the rules of physics and chemistry. Life is chemistry. The protein foldings that we have in all of our proteins are chemical components. Just binding elements together is chemical. This is a virus, this is HIV, and there's a huge debate in the medical science community whether a virus is a living organism or not. But either way, it is protein and receptors and DNA that are all created through chemical bonds. So, what are chemicals made of? Well, when I say chemicals, in this case, I mean atoms. But we know that everything is made of matter. Matter is made of elements, which are also known as atoms. Atoms, elements. Okay, so you have protons, you have neutrons, and you have electrons. And the protons have a positive charge. The neutrons have a neutral, or they don't have a charge at all. And the electrons have a negative charge. Protons and neutrons belong in the nucleus of an atom, and the electrons are anywhere in a cloud around the atom. Now, to make this make sense to you, this is a hydrogen. It has one proton, one electron. We, as human beings, love to organize things. So we conveniently put these electrons on handy little circles around the atom and say that's where the electron is. But in reality, the electron is anywhere and everywhere in this cloud all at once. And if you were to blow up that hydrogen proton so that you can see it with the naked eye, that electron cloud is an entire football stadium. And so the electron is both everywhere in that stadium and nowhere all at the same time, because you can't pinpoint where that electron is in that electron cloud. Now here we have 8 protons and 8 neutrons, which give us a mass of 16, actually. And then you have 8 electrons. So the prevailing theory is that electrons in protons should be the same number. The periodic table of elements. Now, I have met numerous students in my 8 years of teaching, and I will let you know that a majority of you do not have effective chemistry teachers. Nobody's fault. Chemistry is a hard science to teach, and it is very hard to make chemistry clear to the masses. But that makes me have to make it clear to you guys for the purposes of this class. So here is the periodic table of elements with all the different kinds of atoms that exist, whether we created them or whether they exist naturally. So these are our elements. Now, you know the ones in green: hydrogen, carbon, nitrogen, oxygen. CHON here, CHON, those are the 4 elements that make up about 95% of you. You are 95% carbon, hydrogen, oxygen, and nitrogen. And then you have other elements that come into play, like phosphorus, sulfate, sodium, magnesium, calcium, Where is iron? There it is. And a few others, chlorine, iodine. Okay. Anyway, so that's what makes up human life. Now, a periodic table is built in columns, and rows. Okay. The columns show, okay, so here's the elements that make up life: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, sodium, magnesium, potassium, calcium. Okay, you got that? Good. Why was there another noise? Oh, okay. So then let's go back. Oh, that's too much. The rows show you organ elements that all have the same reactivity. Hydrogen has one electron in its valence shell. Lithium has one electron. Sodium has one electron. Potassium has one electron. Rubidium and these two that I don't even know the names of all end up with one electron in their valence shell. 2A has two electrons in their valence shell. You skip all the transitional metals here in the middle because they don't follow any rules. Go to 3 electrons in their valence shell. 4 electrons in your valence shell. Why are we made of carbon? Why are we carbon-based elements? Because carbon can either get rid of enough electrons or take enough electrons to get the electrons it needs in its valence shell, which is 8. So instead, it's willing to form a bond to nearly anything to make those valence shells complete. So, okay, let me finish here. 5 valence electrons, 6 valence electrons, 7 valence electrons, and then, of course, 8 valence electrons, which are our noble gases, and they do not react unless you force them to by pushing energy through them. Okay? So, if I have 1 or 2 valence electrons, I can lose I'm very unstable. You should know. If I only have 1 or 2 valence electrons, and I'll lose them super easy so that I can stabilize. And I'll lose them super easy to the ones that have 6 or 7 valence electrons. So your columns of A or 1 and 2 and 6 and 7 are all your salts. They're ionic salts because 1 and 2 have to lose those electrons super easily, and 6 and 7 are very aggressive in taking these electrons. And it's all so that we have a complete valence shell, right? And so that we are stable. 3, a little bit more difficult to do all that. 5, a little bit more difficult. They have to form multiple bonds, but they tend to be very picky about who they form their bonds with. For example, phosphorus really likes to bond with oxygen. Oxygen only needs 2 bonds, so it'll be like a POH or whatever. But then phosphates are a major functional group for humans. So it's a phosphorus with 3 oxygens on it. And then we get to carbon. I'm not sitting here telling you carbon's a hoe. But if you were to give labels like that to elements, what you need to understand is carbon will bond with anything, because it needs to make 4 bonds to complete that valence electron. We are carbon based because carbon is the most versatile element on this planet because it will bond with nearly anything to fulfill its valence shell. And that is how the periodic table do. Another thing you need to know is electronegativity. It's very low here, and it increases diagonally across and down. So it's very high over here. That's not an exact rule, but it's a very good idea to know. And then going across the rows is adding valence shells. So, no, I'm sorry, that's not right. 1, 2, 3. Going across the rows, what do you do? Just do columns. That's what I know. Right. So there are 25 essential elements that make it life, but the top 4 of them are CHON, carbon, hydrogen, oxygen, nitrogen, and then phosphorus, calcium, sulfur, potassium, magnesium, iodine. It's all in there. we bond through electrons. And once again, it's all about that valence shell of electrons here at the outer edge. Now, this is a noble gas. Its valence electrons are completely full. It has 8, so it's not going to react with anybody. It doesn't need to. It's happy and stable. There's the word valence, if you just don't know what I've been saying this whole time, valence shell. So how does this atom behave? It's happy. It's not going to react. It doesn't need any more electrons, and it doesn't need to lose any electrons. It's super stable. That is a noble gas. But what happens if I have 6 valence electrons, and here I have 2 valence electrons? Both of these atoms are very unstable. So we have to have some chemical behavior that's going to happen to get these electrons onto this atom. This will then have a full valence shell, although it's 1 down, and this will have a full valence shell. These will happily lose these to this atom, and you'll get ions. Whatever this is will be a positive ion, and whatever this is will be a negative ion, because remember, the electrons have a negative charge. So it's actually going to be a 2 negative and a 2 positive because it lost 2 charges. So elements in their valence shell, if you have the same row, same role is the same number of shells. Okay, so all right, just more electrons across. That's what's going on there. Each element has a sequential addition of electrons and protons, and then in the columns I've already talked about, you have the same valence number and you have similar chemical properties. Atoms tend to complete a partially filled valence shell or empty a partially filled valence shell. This tendency is what drives chemical reactions and creates bonds. So here I've lost an electron. This is an ionic bond because this electron was taken from me. Here I am sharing my electrons. This is a covalent bond because we are sharing the electrons. Weak bonds in biology include hydrogen bonds. They're weak individually, but collectively they're incredibly strong, and they're what cause all of the properties of life on this planet, because without water, hydrogen bonds, there would be no life on this planet. And we talk about that. We'll talk about water in a minute. And a hydrogen bond is individually really weak, but it is a partially positive hydrogen bonding to another element that is partially negative. And in this case, this element is oxygen. You have hydrophobic and hydrophilic interactions due to these hydrogen bonds and other chemicals in water. You have van der Waals forces, which is a very weak ionic bond. So the electrons are not fully taken in these bonds. We don't ever really talk about van der Waals, so meh. And then you have strong bonds, which are your covalent bonds. Ionic bonds are actually strong, but van der Waals forces are weak. Weak covalent. Okay, whatever. Covalent bonds are the strongest because you are sharing. You're equals in a partnership. Y'all both are promoting each other equally. You don't want to let go. Don't let go, Jack. It's very stable. It's hard to break a covalent bond. It actually involves energy to do that, which is very important. Okay. You can have multiple covalent bonds. That's not really a thing we need to worry about, but you can have single, double, you can even have 3 pairs of electrons in a triple bond, but those are super rare in the human body. These are very strong bonds. Non-polar covalent bonds are found in oils. Had to think about that one for a second. So sorry. They're found in oils. They're completely full. Their valence shells are completely full. And they won't interact with water very well because they don't need to. Right? So these are our hydrocarbons, which is mostly what you're built out of. Okay, so polar covalent bonds. This is unequal sharing. This is a strong covalent bond, But due to that electronegativity I talked about, where hydrogen has the weakest electronegativity and oxygen's on the other side of that periodic table, so it's much stronger, oxygen actually ends up pulling the electrons towards itself. Even though they're shared electrons, oxygen still gets them a majority of the time. Because this is not equal sharing, oxygen ends up being partially negative because it's holding all those electrons closer to itself, and the hydrogens end up being partially positive. Now, that sounds annoying until you find out that hydrogen bonds are the whole reason life exists on this planet, due to this partial positive and negativity. Hydrogen bonds, it is a weak bond individually. I don't have a videotape, but it causes all the properties of water. And we're still going to go through these slides because I want you to understand water, because as I mentioned so many times already, we are aquatic organisms. So, water. I'm not going to spend a lot of time here. I've told you multiple times, we are water. It's all that life is based on. Life was created in water. All the chemistry of life was created in water. Life doesn't exist without water, which should hopefully make you look around at the current state of things on the planet. Water is inside and outside the cells, and because of these miraculous hydrogen bonds that are formed by water, it creates a sticky molecule. Not sticky like gum sticky or syrup sticky, sticky as in it'll stick to itself. Because water can stick to itself, it becomes incredibly strong, and it gives it special properties. One is cohesion and adhesion. Cohesion is the actual act of water sticking to itself. Adhesion is the act of water sticking to something else. So we know cohesion exists because you can float little things on the surface of water. Bugs can crawl on the surface of water. And when you suck something up a straw, capillary action, when you are drinking through a straw, hopefully water, the water pulls itself up the straw through the vacuum that you have created. It's a good solvent. It used to be called the universal solvent, but we've gone away from that, and we're just going to let you know it's a really good one. Many molecules dissolve in water, and we get these hydrophilic, which is water-loving, versus hydrophobic, water-fearing molecules in the body, which help create that maintaining boundaries issue. Water is lower density as a solid, which is why we don't live on an ice planet. But if it was an ice planet, we would all not be alive. There's a high specific heat. Water stores heat. This is why coastal communities tend to have a much more moderate climate than interior country communities. And it has a high heat of vaporization. It heats and cools slowly. Lots of energy to heat it up, lots of energy to cool it down. Beyond that, that is what you should know about water. Transpiration, which is building on cohesion and adhesion to pull water up and through a tree. Don't have a videotape, sorry. It's the solvent of life. You get hydrophilic water, loving substances, where water will create this full hydration shell around it and completely dissolve it. You can't see it, but I'm making those quotation marks. Completely, quotation, dissolve it, which we know we can recapture it if we get rid of the water. Or it can't form a hydration shell, either because it's way too big or because it's nonpolar. Hydrophobic is usually your fats and oils. They are nonpolar. And hydrophilics are other things. The special case of ice. If ice didn't float, ice would sink to the bottom. The whole of all water would become ice bottom to top. Nothing would live, nothing would be alive. But ice floats because those hydrogen bonds push against each other as ice freezes and pushes the elements farther apart as it freezes. When that happens, ice floats, and therefore it insulates all the water underneath it, letting life continue under the water, even if ice is on the surface. That's what I just said. Specific heat, it takes a lot of heat to cool it up and cool it down, and it moderates temperatures on Earth. This area of the planet will have a much better climate than this area of the planet, although this does have lakes around it, so it's still going to be better than, let's say, middle North America. And it has a high heat of vaporization. So it takes all of this energy, C to D and D to E, for water to fully vaporize, which is a ridiculous amount of constant energy. This allows water to cool us down, and cats and dogs don't have sweat glands like humans do, but they cool down by evaporation off their tongues out of their mouths. Then we get to pH, which is very important to the human body because we have a pH of 7.3. We are so slightly basic. Oh, y'all all basic? Where water splits off from hydrogen, leaving an OH. If the hydrogen ions equal the hydroxide ions, the water is neutral. If the hydrogen ions are greater than the hydroxide ions, water is acidic. And if the hydrogen ions are lesser than the hydroxide ions, water is basic. That gives us the pH scale of 1 to 6 being highly acidic, 2 less acidic, 7 being neutral, and 8 to 14 being less basic to fully basic. And here is our pH scale. Acids eat through us. Bases like sodium hydroxide and oven cleaner are a little bit more nefarious. They actually break the bonds between our cells and slip under our skin and start eating away at the fats and muscles in our body. Either way, they are both very dangerous to us. But then you get to stomach acid, right? We have that in our bodies. You have cola and beer. I don't know how old y'all are. You could even clean with cola. It's so acidic. That's kind of gross. Black coffee, my absolute favorite, by the way. And rainwater. Lots of things can live in rainwater without any treatment. And in fact, in my high school classroom, because for some reason my school isn't over yet, this is 5:29 today, I have about 200 tadpoles that I just keep putting, cleaning their tank with the rainwater that I collect at home. And then pure water and blood is 7. And then we get, more and more and more. You get to the point where you don't want to be drinking ammonia, bleach, oven cleaner, or hydroxide. These help regulate our cells to a pH of approximately 7.3 to 7.4, by buffers. We use a very important chemical buffer in our cells, in our blood, but that is a 2402 topic. So, any questions? Email me at my email and do one brave thing today and then run like hell. Let me see, where am I?